Welcome back to the Math Professor's YouTube channel. If you like the content, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to cover vector addition and scalar multiplication. So we're going to start this in 2 dimensions. And the reason why we do that is I want to show these things graphically, and it's easier to draw stuff in 2 dimensions as opposed to 3 dimensions. But just know that this extends to 3 dimensions quite naturally. So if u is the component form u1 comma u2, and then v is the component form v1 comma v2, then the addition of the 2 vectors is really just the addition of the corresponding components. Now if k is a real number, then k times vector u, or k times the component form of u, is well, what happens is you multiply k to each one of the components. It looks like it distributes to the components here because that's what it does. So graphically, let's talk about addition, and then we'll do scalar multiplication over here. There's 2 ways to look at this. One, they actually say the parallelogram trick or method, and then the other one is going to be the tail to tip method, and they really are equivalent, and you'll see why in a second here. So one way to think about this is if I want to do the addition of u comma v, I can set up a parallelogram that has vector u and also vector v. So what I'm going to do is vector u is going to go up here, and then vector v is going to go right here, creating that parallelogram. I wish I had drawn that a little bit better. I won't attempt to. That's better. So what's going to happen is the addition of u plus v is going to be this main diagonal of this parallelogram. So it's going to start at the initial points at both and end at the terminal points at both. So this right here is vector u plus v. Now another way to do this is you can use the tail to tip method, and what they're saying is that if you start with vector u and then you take vector v and move it to the tip of u, so I'm going to take that vector v and I'm going to move it over to here, so this is vector v, then that resulting vector is going to be from the tail of u all the way to the tip of v. So this is going to be that u plus v. And what we can see is, the pictures give you that same u plus v. Now what does scalar multiplication do? So if I have vector of u, let's call it, let's do it back here. So if I have vector u, which looks like this. Now if I multiply this by k, what it's going to do is it's going to multiply each of the components by k, which really is going to stretch the vector by k. So this vector right here would be equal to k times u, where if, say, this is length 1, this will now be length k. So it's going to multiply each component by k, so it's going to stretch it by a factor of k. So what it's going to do is it's going to keep the same direction, it's just going to be a stretch. Now if k is negative, it's going to actually flip it to the other side, so it's just a stretch in the opposite direction. Alright, so what I've given is 2 vectors in 3 dimensions, and I want to do some operations on these things using, what was described before. So if u is going to be 2, 0, negative 5, and v is negative 1, 3, 7, can I do a linear combination of the 2 vectors? So what I have is I have 3 times the vector 2, 0, minus 5, because that is u, plus 2 times the vector negative 1, 3, 7. So just like we do with arithmetic, we're going to handle the multiplication first and then the addition second. So distributing these 3 to the first vector and the 2 to the second vector, I'm going to get, 3u is going to be multiplying all the components by 3, so this is 6. 3 times 0 is 0. 3 times negative 5 is minus 15. Plus, distributing this 2 to these components, I have negative 2, 6, and 14. Now in order to add the vectors, we just add the corresponding components, so 6 minus 2 is going to give us 4. 0 plus, 6 plus a negative 2 is going to be 4. 0 plus 6 is going to give us 6. And then negative 15 plus 14 is going to give us negative 1. Now if I can add the vectors, I can also subtract the vectors. And one way to think about this is u minus v is, by definition, this is going to be u plus, negative 1 times v. That's really what subtraction is. We're just multiplying by the opposite of its sign. Sorry, we're adding the opposite of its sign. So let's do this as in terms of what we did in 1, or a. So this is going to be 2, 0, minus 5, and then I have plus a negative 1 times the vector negative 1, 3, and then 7. So the first vector is not being multiplied by anything, so we leave that alone, and then I'm going to change the signs of the second vector. So this is going to be 1 minus 3, 7. So now we can add. So 2 plus 1 is going to be 3. 0 plus negative 3 is going to be minus 3. And then negative 5 plus 7 is going to be 2. Now, you could probably ask, like, hey, could I have done that without, writing this? Well, of course you can. So, 2 minus a minus 1 is 3. 0 minus 3 is negative 3. And then minus 5. This should have changed. This is a minus 7. I'm glad I caught that. Changed to the sign of 7. So then 5 plus a negative 7 is going to be minus 12. Minus 12. So then we check it. 5 minus 7 is minus 12. So it does work out. Then last, I want to find the magnitude of 2u. So the first thing I'm going to do is let's go ahead and find 2u, and then we'll find the magnitude of that. So see, what is 2u? Well, 2u is going to be 2 times 2, 0, 5. So multiplying this together, we're going to have 4, 0, and then this is going to be 10. So the magnitude of 2u is going to be equal to the square root of the sum of the squares of its components. So this is 4 squared plus 0 squared plus 10 squared. So this is going to be the square root of 16 plus 100, or the square root of 116. Now, we know that 116 is divisible by 4 because the last two digits are divisible by 4. I want to show you an interesting property. So 116 divided by 4 is going to be 29. So this is the same thing as the square root of 4 times 29, which is actually 2 times the square root of 29. So kind of an interesting property here is that the magnitude of 2 times u is actually the absolute value of 2 times the magnitude of v. And let's go ahead and test this property here. So the absolute value of 2 is going to be 2, so that will be 2. And then when I have the magnitude of the initial vector, this is going to be the square root of, well, 2 squared plus 0 squared plus minus 5 squared. Oh my gosh, I will try not to make so many mistakes, but it doesn't matter, it's still 100. Minus 5 squared. So this is going to be 2 times the square root of 4 plus 25, which is actually 2 root 29, which is the same thing. So here's the properties of u, v, and w being vectors, and a and b being scalars. So the first one says that addition is commutative. U plus v is equal to v plus u. This also says that it has an additive identity. So if I do u plus the 0 vector, so say u1 comma u2 plus 0 comma 0, well, we know when we add the corresponding components, you're just going to get u1 plus 0, v1 plus 0, or just u1, v1. I'm sorry, u1, u2, so it's just going to be u. This one says that it's associative. So you can, the order in which you add doesn't matter. That if you add u plus v first and then add w last, it's going to be the same thing as adding v plus w first and then u last. It also says that it has an additive identity. So what this one says is if I have a vector u, which is going to be, say, 1 comma 2, well, there exists a negative u, which would just be the opposites of these things. So when I add these things, so negative u would just be negative 1, negative 2. And if you add these two vectors, you're going to get the 0 vector. 0 times u is going to be equal to 0. So if I take a scalar 0 and I multiply, let's just say that 1 comma 2 again, well, when we distribute this through, this is going to be 0 times 1, and this is 0 times 2, giving us, well, 0 comma 0, which is the 0 vector. So we have to be careful of the difference between the 0 scalar which is a whole number, and the 0 vector, which is going to be components. So I should write them like this, just to verify that we're talking about vectors. The scalar 1 times u is going to be u, so very similar. If I multiply this by 1, it's going to unchange u. Also says that multiplication, well, scalar multiplication is associative, so I can multiply u times b first. U times b first, and then multiply by the scalar a, or you can multiply the scalars first and then multiply by the vector last. They're distributive, so scalars are distributed over vectors. So a times the sum of u plus v is a times u plus a times v. And also vectors are distributed over the sum of scalars. So a plus b times u is a times u plus b times u. Last, I want to really verify the I, j, k notation for our vectors. So a unit vector is a vector of length 1, and I want to start out with our standard unit vectors. So the vector I is going to be 1, 0, 0, and I know when I find the magnitude of this thing, say the magnitude of vector I is going to be the square root of the first component squared plus the second component squared plus the third component squared. So this is going to be the square root of 1, which is equal to 1. Very similar, if I do it with j and k, we're going to get 1 as well. So we can tell that these things have unit length. Now my claim is that any vector v, which is v1, v2, v3, we're just going to do this in 3 dimensions, can be written as a linear combination of the standard unit vectors. And the way I can kind of show that is if I have v1, v2, v3, well, this is the same thing as the sum of 3 vectors, where I can just kind of isolate the components. So v1, 0, 0, plus 0, v2, 0, plus 0, 0, v3. And I know when I add these things together, I'm going to get this vector. Now, what I can do is I can factor a v1 out of this first one. So v1, this is going to be 1. Factor v1 out of 0 is still going to be 0, and this is going to be 0. So I can tell if I distribute this over the vector, we're going to get this vector here. So similar, I can factor out a v2, and then also a v3. So when I do that, I know that this is vector I, this is vector j, and this is vector k, so I can rewrite any vector as v1i plus v2j plus v3k. So a quick example is, let's rewrite the vector in terms of the unit vector of the standard unit vectors. Now this idea gets expanded a lot in linear algebra. I highly recommend you take it. It's super cool. So these are what we consider a basis of this three-dimensional vector, and I like to think about it as kind of like Lego building blocks. That if I have any vector, say u is equal to, I don't know, 5, -1, 4, then what I know is that this is going to go 5 in the x, -1 in the y, and then 4 in the z. So those are kind of like the Legos that you need. So what I know is this has to go 5 in the x, or 5 in this direction, -1 in this direction, and then +4 in this direction. So it really is as easy as it looks, that you can simply write this in this way instantly without any proof. So the last thing I want to do is I want to write a vector in terms of its length and its direction. So I want to be able to, like, how do we build a unit vector, and how do we write it as its length times its direction? So a vector's direction is the unit vector in the same direction as, as the vector. So if v is a vector, then the unit vector in the direction of v is computed by v over the magnitude of v. So we're going to guarantee that this thing is a unit vector. I know it's in the same direction of v is because I can rewrite this as 1 over the magnitude of v times v. And really this is nothing more, this piece right here, this 1 over the magnitude of v is nothing more than a scalar. So I have a scalar times the initial vector, so I really just have a stretch of that vector. And that stretch is going to take a vector and it's going to squish it down to a unit vector. So to write a vector in terms of its length times its direction, well, vector v is equal to, well, the magnitude of v times, that computed unit vector. And we can see that these magnitude of v's would cancel, so then you're just going to get v is equal to v, or vector v is equal to vector v. But this is going to be its length, and this is going to be its direction. Length being the magnitude of v, the direction is, computed right here. So here's our vector v, and I wrote it in terms of the standard unit vectors, so 2I plus 2j minus k. And I want to write this in terms of length times direction. So first, let's find its length. Well, the length is denoted by the magnitude of v, which is going to be the sum of the squares of its components. So 2 squared plus 2 squared plus 1 squared. So 4 plus 4 plus 1 is going to be the square root of 9, which is going to be equal to 3. So the magnitude of v is 3. Now its direction is computed by v over the magnitude of v. V being the initial vector, so I can write this, if you prefer its component form this way, or if you prefer the ijk form, it doesn't matter. So this is going to be all over 3. So I can rewrite this as 2/3, negative 1/3, or if you like the ijk, k, you could do 2/3 I plus 2/3 j minus 1/3 k. It doesn't matter. They're equivalent. So then when I want to do length times direction, so if I have length times direction, I can say that vector v is equal to 3 times this vector. So 2/3 I plus 2/3 j minus 1/3 k. Now this will become useful finding these unit vectors later in your Calc 3 class, especially when you're trying to find like directional derivatives and later when you're doing vector fields. So they will become extremely useful. So if you like the content, please subscribe. Thank you.